Hi, this is day 44 and it is brought to you by the symbol for parallel, because what we're going to do today is take more of a look at resistances in parallel. And before we do anything else, just want to remind you that the key to any circuit is, of course, Ohm's law. V is equal to I times R. And when you're using Ohm's law, remember that if you're talking about a certain resistance, this has to be the voltage for that resistance, and this has to be the current for that resistance. You can't be talking about one resistance and use a current or voltage from some other resistance. Okay, keeping that in mind, let's take a look at this circuit here. And what we want to do in this circuit is we want to figure out the current and the voltage drop across every single resistance. Okay, we've got 1, 2, 3, 4, 5 resistances. We want to figure out the current and the voltage drop through every single one of them. Okay, how can we do that? Well, I'll tell you what. Let's start off with this one. All these other resistances, they are inside some parallel branches. This one is outside of those parallel branches. So let's start off with this one, because it's kind of sitting there all alone by itself, ready for the picking. Okay, so let's apply Ohm's law to this resistance right here. Well, the voltage drop across the resistor, that's what we're interested in, is going to equal to the current through the resistor. That's going to be I.P., the total current coming from the source, times the resistance itself. Okay, now by the looks of this, we're going to have to figure out one of these two things a different way, because you can't figure out two unknowns with one equation. So how about this one? I think we can probably figure out this one some other way. How about this? Suppose we say the total potential drop for the whole circuit is going to be equal to the current through the whole circuit times the equivalent resistance for the whole circuit. Okay, the total potential drop through the whole circuit is going to be equal to the current through the whole circuit times the equivalent resistance for the whole circuit. All right, what's the total potential drop through the whole circuit? Well, you've got a total potential increase of 12 volts here. That means the total potential drop through the whole circuit is going to be 12 volts. What's the total current through the whole circuit? Well, that's IT. You know, the same current through the 1 ohmer, the resistance we're really interested in. Okay, that's good. What's the total resistance for the whole circuit? Well, how about this? If we imagine these 3 parallel branches as one big resistance, as one big parallel mess. Don't know what that is in the moment, but that's okay. The equivalent resistance for the whole circuit is going to be 1 ohm plus the resistance of the parallel mess. Can everybody see that? Okay, if you look at this circuit as a whole, what do you have? You have a 1 ohm resistor, and then in series with that, coming right after that, you have a big parallel mess. So the equivalent resistance of the whole circuit is going to be 1 ohm plus the parallel mess. Right? If you have 2 resistances in series, okay, and if we treat the parallel mess as one big resistor, then we have 2 resistances in series. So there's the equivalent resistance of the whole circuit. Okay, the 2 resistances in series, the 1 ohmer plus the parallel mess added together. Okay, the question is, what's the parallel mess equal to? Let's see if we can figure that one out. So, when you're talking about a bunch of resistances in parallel, 1 over the equivalent resistance. That's going to be 1 over the parallel mesh. That's the equivalent resistance of all these three things in parallel that we're talking about, is going to be equal to 1 over the resistance in the first branch, which is 1, plus 1 over the resistance in the second branch, which is 5, plus 1 over the resistance in the third branch, which is, well, in total, 3 plus 2, 5 ohms. Okay, so there we go. We can solve this equation for our parallel. 1 over 1 is 1, 1/5 is 0.2, 1/5 is 0.2. So 1 over our parallel is going to equal what? 1 plus 0.2 plus another 0.2, 1.4. So if you flip this side over, you're going to get our parallel. And if you flip this side over, well, there's an imaginary 1 down there, you're going to get 1 over 1.4. So our parallel is going to be equal to 1 over 1.4. That's 10/14. That's 5/7. That is 0.71 ohms. Okay, so our parallel, 0.71 ohms. So we can substitute in over here now for our parallel. That is going to be 0.71 ohms. So what's IT going to be? Well, you solve this equation. This is 1.71. You take it over to the other side and you get 12 divided by 1.71. Let's see what that works out to. 12 divided by 1.71 comes out to, round it off, 7 amps. Okay, so we know that this current, the current through the 1 ohm resistor, is 7 amps. That's one of the things we're supposed to figure out. And now we can figure out the voltage across the 1 ohm resistor pretty easily. Just come over here, IT is equal to 7 amps multiplied by 1, there you go, 7 volts. So this voltage drop right here is going to be 7 volts. Okay, let's start figuring out some other things. Okay, let's make ourselves some room here. Let's see if we can do this resistor now. What's the voltage drop across this resistor? The voltage drop across this resistor is super easy. Take a look. Remember, when you look at a circuit like this, what I want you to see is not one big complicated circuit. I want you to see 1, 2, 3 separate, 3 individual circuits. Okay, so let's consider this circuit right here. Okay, remember, in any circuit, the voltage increase is going to be equal to the voltage decrease. The voltage increase is going to be equal to the voltage decreases. Okay, so basically, you're gaining 12 volts over here. That means as you go around this circuit, you got to be losing 12 volts. If you're losing 7 here, well, over here you're going to have to be losing 5, right? Everybody sees that. In any circuit, the increases are equal to the decreases. The gains are equal to the losses. If you gain 12 volts here, you got to lose 12 volts through the rest of it. If you lose 7 here, you're going to have to lose 5 here. So V2 is going to be equal to 12 take away 7, which is equal to 5 volts. So let's write that in there. That's 5 volts. Now let's figure out I2, okay, the current through this resistor. Well, again, you can just use Ohm's law to do that. You can say the voltage drop across a resistor is equal to the current through the resistor times the resistor itself. And well, 5 times 1 is equal to 5. So I2 is going to be equal to 5 amps. I2 is going to be equal to 5 amps. Okay, can we figure out I3 and I4? Those ones are actually pretty easy to do. You can do them by symmetry. Take a look. You've got 5 ohms in this branch and 5 ohms in this branch. So as far as the electrons are concerned, these two branches are equivalent. Okay? They're going to have the same current in each. Take a look. You've got 7 amps coming along here. 5 amps disappears down this way. That means there's got to be 2 amps left. Right? Everybody agree with that? 7 amps coming along here. 5 amps takes off this way. That means there's got to be 2 amps here. These two branches are the same. 5 ohms here, 5 ohms in total here. That means, without doing any calculation, you know that these 2 amps, they're going to be split equally. I3 is going to be 1 amp. And I4 is going to be 1 amp. And I'll tell you what, we can check that later if you like. But for now, let's see if we can figure out what V3 is. Okay. Well, again, the voltage drop across this 5 ohm resistor. Again, what I want you to see here is not one big ugly circuit, but 1, 2, 3 separate individual circuits. Let's concentrate on this circuit right here. The voltage increase through the circuit is going to equal to the voltage decreases through the circuit. If you gain 12 volts, that means as you're going around this circuit, you got to lose 12 volts. So you gain 12 here, you lose 7 here, that means you got to lose 5 here. V3, it's going to be equal to the difference between 12 and 7. V3 is going to be 12, take away 7, that's going to be 5 volts. Okay. And yeah, if you like, if you want to check out I3, make sure it's the same. Okay. You can just apply Ohm's law. You can say the voltage across a circuit, or pardon me, the voltage across a resistor is equal to the current through it times the resistance itself. And sure, 5 is equal to 1 times 5. You can figure out I3 that way and get your 1 amp like that. Okay, let's do the last branch. First of all, what's the current through both these resistors? Well, it's going to be the same, right? You start off with 7, you lose 5, you lose 1. So yeah, there's going to be 1 amp left going through these. Okay, what's the voltage drop across these resistors? Well, let's do the voltage drop across this resistor first. Again, Ohm's law is probably a good way to do that. The voltage drop across a resistor is equal to the current through it, which is 1 amp, times the resistance itself, which is 3 ohms. So what do we got? 1 times 3, V4 is going to be equal to 3 volts. Okay. What's V5 going to be? Well, you can do V5 a couple ways. Okay. Here's one way to do it. You could say, okay, on this circuit here, if I'm an electron, I'm going around this circuit here, I'm gaining 12 volts. That means I got to lose 12 volts. So I gain 12 here, I lose 7 here. That means between here and here, I got to lose 5 in total. So this is going to be, well, 5 take away 3. V5 is going to be 5 take away 3, which is equal to 2 volts. Okay. If you like, you could also get V5 using Ohm's law. You could say again, the voltage drop across a resistor. Pretend we don't know what that is. Again, the voltage drop across a resistor is equal to the current through it, which is 1 amp, times the resistance itself. And there is another way to get V5, 2 volts. Don't forget, you can also use ratios if you have resistances in parallel, if you have resistances in series, you can also use ratios to figure out the voltages. And you can see the ratios work out here. 3 is to 3 as 2 is to 2. Okay, and that is it. Again, just remember, when you're doing something like this, okay, and you're using Ohm's law, whatever resistance you're talking about, well, this has to be the voltage for that resistance, and this has to be the current for that resistance. And also, when you're looking at something like this, don't see one big ugly circuit. Make sure you take a look and you see 1, 2, 3 separate circuits. And for each one of those separate circuits, the voltage increase is going to equal the voltage decrease. And if you keep all those things in mind, you should be okay when you do your assignment. And as far as your assignment is concerned, whichever one you got with the last video, just keep working on that. You can finish all those questions on that resistances in parallel assignment. Before you go, let me ask you one quick question. Suppose I say, okay, I'm going to apply Ohm's law to this resistance right here. If I treat all these resistances as one big resistor R parallel, and I'm going to apply Ohm's law to this one big parallel mess here, R parallel, what voltage do I use? What current do I use? Okay. Think about that for a sec. What do you figure? Remember, if you're doing Ohm's law, the current has to be the current through the resistance. So if you treat this as one big resistance, what's the current through it? Well, you've got 7 amps coming in and 7 amps going out. So your current would be IT, this 7 amps. What voltage would you be using? Well, again, it should be the voltage across his resistance. So if you treat this as one big resistance, as you go around the circuit, you gain 12 volts, you lose 7 volts. That means through this one big resistance, you're going to lose 5 volts. So if you're applying Ohm's law to R parallel, this one big parallel mess here, there's how it's going to look. And if you actually make the substitution, R parallel is equal to 0.71. Okay. I'm not sure what that works out to, but it is pretty darn close to 5, which is good. All right, I will leave you alone and you can get going on your assignment. Good luck with that. Keep at it. Come back to the video, pause, wherever you need to. We went over a lot of stuff here, but when you really get down to it, this circuit stuff, on the one hand, it can look kind of complicated, but on the other hand, once you really start thinking about it and really start breaking it down into individual simple circuits, it's not so bad. So good luck with that assignment, work hard at it, and these things will actually start to come fairly easily. Bye for now, we will see you again soon.